So a very quick review of quantum mechanics. I'm assuming that you're all familiar with the basic axioms of quantum mechanics. I like to write the axioms in 3 parts. I don't know if that's the same structure that you are familiar with, but I would put it in this way. The first aspect of quantum mechanics is that we associate with an isolated quantum system, we associated Hilbert space. So associated with an isolated system is a complex Hilbert space. Now a state of the system, and strictly speaking sort of a pure state, because we'll start to talk about so-called mixed states today, but a pure state of the system corresponds to a vector in Hilbert space. Strictly speaking, you know that global phases don't play a role. When you calculate expectation values, then overall phases cancel out. So in fact, the pure state of a system is characterized by a vector modulo an overall phase. So another way of putting it is to say that a pure state corresponds to a one-dimensional subspace of Hilbert space. Let me write this down. A pure state, of course, is the most accurate description that you can have of the state of a quantum system. So let me put it in this way, that a most accurate description of the system corresponds to a one-dimensional subspace of Hilbert space. And now in practice, what you do, you take a unit vector psi, which spans this one-dimensional subspace, and you say this is the state of the system. So this is what is called a pure state. This, I would say, is part number 1 of quantum mechanics. Pure states are vectors in Hilbert space. Next, we should talk about observables. Now, observables are represented by Hermitian operators acting on this Hilbert space. So observables are represented by Hermitian operators. Now, a Hermitian operator has a so-called spectral decomposition. It's the following. I take an observable A, it's a Hermitian operator, and I can always write it in the following form. It's the sum over I, little ai, where this little ai, or these little ai, are the eigenvalues of my observables, multiplied with the projector pi, and this is the projector which projects onto the associated eigenspace corresponding to that eigenvalue. Perhaps you haven't seen it in this form with the projector, but you've perhaps seen it in a slightly different form, where you write this as ket and bra. Maybe you've seen it in this form. This is the form that applies when the eigenvalues are non-degenerate. In that case, you can always decompose a Hermitian operator in this form, sum over I, eigenvalue, and then the ket, that's the associated eigenvector, and then bra, the associated eigenvector. And what I wrote with the projection operator, that is a generalization for the case that some of the eigenvalues might be degenerate, because then you have associated with an eigenvalue, you have not just one eigenvector, but you have an eigenspace. If this eigenvalue is degenerate, then you might have a 2 or 3 or higher dimensional eigenspace associated with that. Yeah? Now, so much about the representation of observables. What is now, given a pure state psi, what is the probability of measuring a certain eigenvalue of a given observable? So what is the probability of measuring the eigenvalue AI in a given state psi? And again, I write it in the in the more general form that allows for the possibility that eigenvalues are degenerate. In that case, this probability is given by the expectation value of the projector Pi. And you certainly recognize in the non-degenerate case, if again you replace the projector Pi simply by this ket bra II, then you recognize this is nothing but the scalar product of psi with I, with eigenvector I, absolute value squared. And that's, I'm sure, the form that you are familiar with. So what I wrote here is a slight generalization. I will actually come back to this form and explain it a little more, because I would like to say a little more about projection operators. This is known as the Born rule. That's how you calculate probabilities. What's the expectation value of an observable A? This is, of course, you take the bracket combination. This is the expectation value. And then if you insert the spectral decomposition of the observable A, then you can also write it in the form sum over I, AI, and then psi, Pi, psi. And in this form, you immediately recognize that the expectation value of the projector, Pi, that must be the probability of measuring eigenvalue AI. And the final aspect that's still missing here is what happens to the state after a measurement, post-measurement. If prior to measurement you have pure state psi, and then you measure eigenvalue AI, then subsequently you find the system in an eigenstate of the observable A, namely an eigenstate corresponding to the measured value AI. So you are in the, you take the original state psi and you project it onto the eigenspace. I'm talking general again, allowing for degeneracy. So you take the original state and you project it onto the eigenspace of the eigenvalue that you measured. So you apply a projection operator Pi to your original state, and then it's projected onto an eigenstate, onto the eigenspace. And then you have to make sure that the new state is normalized. So you have to, for normalization, you have to divide by the square root of psi, Pi, psi. And this ensures that the new state is again normalized. And then there's one part still missing. We've talked about states and observables and probabilities and expectation values. We have not yet talked about how the system evolves in time. So this is the third part, that closed systems evolve in time via unitary transformations. So if initially at some time 0 I have pure state psi of 0, then after time t I have psi of t, and I obtain that by applying a unitary time evolution operator u of t to my initial state psi of 0. What I can do, I can take on both sides of this equation, I can take the time derivative and I get it in differential form, and then also with the usual conventions, constants f minus h bar over I, d over dt, psi of t. And this is some Hermitian operator, which is called the Hamilton operator, acting on psi of t. So this is the differential form for time evolution. That's the Hamilton operator. And this is basically quantum mechanics on one page. I would like to look at the simplest quantum system that you can imagine. And the simplest quantum system that you can imagine is a two-level system. So it's in a two-dimensional Hilbert space. So two-level system means that the Hilbert space dimension is equal to 2. And this is actually quite relevant because there are many physical systems that you can describe as two-level systems. For example, a spin 1/2. If you have an electron and you are only interested in the spin degrees of freedom, then you have spin up or down. It's a two-level system. There are atoms that you can effectively describe as two-level systems. Of course, atoms have more than two levels, but you may be in a situation where, say you have the ground state, for example, and then you only excite the first level above the ground state, and all the other levels are never excited in your experiment, so you can disregard them, and you can effectively, for the purposes of your experiment, you can effectively describe the atom as a two-level atom. Another example is our photon polarizations. Photons have, of course, the usual spatial degrees of freedom, but they also have polarization degrees of freedom. And there are two possible polarizations of a photon. And if you're only interested in the polarization degrees of freedom, then this is a two-level system. And nowadays, there's this whole new exciting field of quantum information, quantum computing. And the basic information carriers are so-called qubits, so quantum mechanical bits. And qubits are nothing but two-level systems. To develop the whole theory, one uses abstract qubits without reference to the specific physical system, how they are realized. In an experimental realization, these could then be spin degrees of freedom, photon polarizations, and so on, magnetic flux quanta, and whatever you like. But the whole theory of quantum information is developed in terms of qubits. And for this reason, two-level systems are extremely important in today's physics. Now, in this two-dimensional Hilbert space, you can introduce an orthonormal basis. And now, depending on the system that you are considering, if you are looking at spins, for example, then very often one uses as basis vectors the up and down states. If, on the other hand, one does quantum computation, then in an analogy to classical bits, one uses 0 and 1 states. Now, if this is your basis, then a general pure state of a two-level system is a linear combination of these basis vectors. So an arbitrary psi can be written as a linear combination of basis vector 0 and basis vector 1, where the absolute value squares of the coefficients must add up to 1. And as I mentioned before, overall phases are irrelevant. So a general pure state has this form up to an irrelevant global phase. There's a nice pictorial representation of the states of a two-level system, and this representation is the so-called Bloch sphere representation. Why is that? Let me continue with the general form of a pure state. It's a linear combination of 0 and 1. And we know that the sum of the absolute value squared of the coefficients must be equal to 1. And one way to achieve that is we can write the first coefficient as a cosine of some angle theta half by convention, and the second coefficient as a sine of the same angle. Then automatically we have ensured, since sine squared plus cosine squared is equal to 1, automatically we have satisfied the normalization condition. Now, of course, the coefficients can be complex. They are not necessarily real. So in front of the sine and the cosine, we have an e to the I some angle. But we say that the overall phase is not relevant. So we can factor out the phase, say, in front of the cosine, and only retain a phase factor in front of the sine. So this is a relative phase. So let me note that what we have done is we have factored out a global phase, which is irrelevant. And we've done it in such a way that this first coefficient is real. We don't have any phase in front of the first coefficient. Here, on the other hand, we have a relative phase where the phi is somewhere between 0 and 2 pi. And the theta, where we want to cover with our sine and cosine, we would want to cover all values between 0 and 1. And so as for the arguments, we should be in the range between 0 and pi over 2. And since we have a 1/2 in the argument, the theta must be in the range between 0 and pi. And in this way, we can cover, for the coefficients, we can cover the whole range between 0 and 1. So we have a representation of a pure state of a two-level system in terms of two angles. And this provides a way to represent that graphically. Let me sketch a coordinate system, x, y, and z. And let me try to draw a sphere. And let's look at an arbitrary point on the surface of that sphere. It's a unit sphere, I should say. And let's consider a point on the surface of that unit sphere. In spherical coordinates, we can describe this point by two angles. We have the angle theta, and we have, when we project this vector onto the xy plane, then we have another angle measured from the x-axis here, another angle phi. And you see in spherical coordinates, the angle theta takes values between 0 and pi, and the angle phi takes values between 0 and 2 pi, just like the angles that we have above in the parameterization of our pure state. So you see there's a one-to-one correspondence between pure states of a two-level system and points on the surface of a unit sphere. So pictorially, we can say a pure state psi of a two-level system is a point on the surface of a unit sphere. And this sphere is called the Bloch sphere. So we have here that the correspondence, pure state corresponds to point on the surface of the sphere. The basis state 0, if you look above, the basis state 0 corresponds to angle theta equal to 0, because then the cosine is 1 and the sine is 0. So in this pictorial representation, the basis state 0 corresponds to the north pole of the sphere, and the basis state 1 corresponds to angle theta equal to pi, because then the cosine vanishes and the sine is equal to 1. So the basis state 1 is the south pole of the sphere. And they are orthogonal to each other, and they are on opposite sides of the sphere. They're so-called antipodes. And this is true generally, that mutually orthogonal states correspond to antipodes. And finally, when you apply a unitary transformation to a pure state, then this means that you move on the surface of this unit sphere. And you can show, I'm not going to do this here, I'm just telling you without proof, that there is a one-to-one correspondence between unitary transformations in a two-dimensional Hilbert space and rotations. So we have correspondence between unitary transformations and rotations. There are three Pauli matrices that sometimes they are sigma 1, sigma 2, sigma 3, or other people say the sigma x, sigma y, sigma z. So the first one is 0, 1, 1, 0. The second one is 0, minus I, 0. And the third one is 1, 0, 0, minus 1. Sometimes people introduce a fourth Pauli matrix sigma 0, but this is nothing but the 2 by 2 unit matrix, and this is 1, 0, 0, 1. Some basic properties: all of these matrices are Hermitian. All of these matrices, when you take the square, they give the unit matrix. When you multiply two Pauli matrices, sigma I and sigma j, then you get sum over k going from 1 to 3. Now I is not the index, but it's the imaginary unit, I, and then the Levi-Civita symbol, epsilon ijk sigma k, and this holds for I different from j, and the indices are going from 1 to 3. I had promised to you that I wanted to tell you a bit more about projectors. What is a projector? Let's start with the simplest case, which is the projection onto a one-dimensional subspace, which is spanned by some unit vector. So let's consider a projector onto a one-dimensional subspace spanned by a unit vector chi. In that case, the projector, the associated projector, has the form, it's the ket bra chi chi. If, on the other hand, you have a higher dimensional space onto which you want to project, so you have a projector onto a higher dimensional subspace, spanned now not by a single vector, unit vector, but by some orthonormal basis. So spanned by the orthonormal basis, let's say phi n, then the projector becomes sum over n, and now again the ket bra phi n phi n. So this is the situation where you have Hilbert space. Let's say the Hilbert space is three-dimensional and real, so that I can draw it. I have a three-dimensional space, and let's say that there is an orthonormal basis phi 1, or there are two unit vectors phi 1, phi 2, they are orthogonal to each other, and they span the two-dimensional subspace of your three-dimensional space. Now, what I want to achieve is the following. If I have an arbitrary state psi, then I want to have a projector P, projection operator P, that projects the original state psi onto this two-dimensional subspace. And I claim that the projector, as defined above, achieves that. So this projector has the effect that an arbitrary state psi is projected onto this two-dimensional subspace spanned by the phi n. The projectors that I introduced above, they have a number of useful properties. They are Hermitian, they are idempotent in the sense that when I apply the projector twice, a second time, then nothing happens. That's in a way the defining property of a projector. When I have a vector, I project the vector onto a subspace, then it's in the subspace, and then I apply the projector again, then nothing should happen because it's already in the subspace. And finally, the trace of the projector equals the dimension of the subspace onto which I project. I would strongly encourage you, as a homework, that you check these properties for this projector that we defined above. So take this definition of the projector, use the fact that the phi n are an orthonormal basis, and check that this projector satisfies the three properties that I listed here. So why did I dwell on projectors? Because projectors feature in different places in quantum mechanics, and we've already seen one instance of that, namely in the context of measurement. As part of our axioms, I had written that the probability of obtaining an eigenvalue AI in a state psi, so probability of measuring AI given, let me write it in this probability notation that we also used yesterday sort of as a condition the probability of measuring AI given a pure state psi. This was the expectation value of the projector Pi in the state psi. Just a slightly different notation here, but it's this psi, Pi, psi that we had before. So how can you interpret the projector here? You can in a way regard the projector here as a proposition, as a statement, in the sense of statistics also that we discussed yesterday. The projector corresponds to the statement, I measure eigenvalue AI. And the probability that this statement is true equals the expectation value of this projector. So this is one way of interpreting projectors. Another context where you can use projectors is to describe a pure state. Remember, the expectation value of an arbitrary observable A in a pure state psi, this is the operator A sandwiched between the two psis. But you can also write that as the trace of psi A. Okay, let me show you why this is the case. Okay, let's look at this expectation value of A. What we can do is we can insert an orthonormal basis. We can write that as psi A J psi. We can change the order of our product. We can write it as sum over J psi A J. Yeah, I just switched the order of the two scalar products. But what is the trace? It's the sum of the diagonal elements of a matrix. Or more general, here say the trace of an operator, let me call it B. This is sum over J B J. Okay, that's a trace. But now you recognize when you look at the expression on the right-hand side, this has precisely the form of a trace. We have sum over J, and then something in the middle, and then on the right we have a cat, J again. So what's written here, this is nothing but a trace, namely the trace over what's in between the two J's. So it's the trace of psi A. But now we learned that this object here, the bra cat bra psi, this is nothing but a projection operator onto a one-dimensional subspace, namely the subspace spanned by psi. So in other words, we can write the expectation value of the observable A in the pure state psi, we can write as the trace of projection operator associated with the state psi times the observable A. So we have the projection operator featuring two times. We have it featuring here, and we have it featuring here. In the first case, the projection operator can be regarded as a statement about the result of a measurement, and in the second case, the projection operator can be regarded as representing a pure state. And this opens the possibility that we represent a pure state not as a vector psi, but as a projector, p psi. And this has the advantage also that this issue of the overall phase disappears, because the projector, that's the ket bra psi psi, and if we multiply psi with an overall phase, then this cancels out when we construct the projector. If we multiply psi with, say, e to the I phi, then the ket is multiplied by e to the I phi, but the bra is multiplied with the complex conjugate, that's e to the minus I phi, and so these two factors cancel, and we have automatically gotten rid of this issue of the global phase. And the key reason why I introduced this form here is, of course, because it makes the transition easier to a new concept, which is the density matrix. The density matrix will turn out to be the generalization of the projector. It's time to move on from pure states to mixed states. Why do we need mixed states at all? Why can we not simply work always with pure states? And what is a mixed state? A mixed state is obviously different from a pure state in the sense that it cannot be represented by a Hilbert space vector. I would like to give you 3 reasons why one needs mixed states. The first reason is, quite generally, I don't know to which extent in the quantum mechanics course you talked about also interpretational issues of quantum mechanics and the way that Niels Bohr phrased the axioms and the foundation of quantum mechanics. He always emphasized that every concept must be characterized in terms of experimental procedures. We must always specify how we prepare a system, how we measure a system. And a pure state is, when we describe a system by a pure state, then explicitly or implicitly what we always mean is that behind that statement there's an experimental procedure specifying how we prepare that state. And it turns out that there are experimental procedures or experimental setups that simply do not give rise to a pure state, but that give rise to a mixed state. So this is reason number 1, that mixed states correspond to experimental setups that simply do not give rise to a pure state. Another reason that I would like to give you is that when you look at larger systems, composite systems, systems that are composed of several parts, and then you wonder, how can I describe a subsystem? How can I describe just one of these several parts? Then it turns out that by necessity you will need mixed states to describe a subsystem. Even if the total system is in a pure state, as soon as you want to describe just a part of the system, then this constituent is generally not in a pure state, and by necessity you will have to resort to mixed states. So mixed states, in other words, they arise by necessity when you describe subsystems. And we'll talk about the concept of a so-called reduced state. And then a final reason that I will just mention without proof, but maybe it's appealing to some of you who are more sort of conceptually minded. There's also a conceptual reason. You can formulate certain very basic requirements that a physical state should satisfy. Very general, in a very general way. And you can wonder what's the most general form of a state that satisfies these basic requirements. And that turns out to include mixed states. Yeah? So this is comes from the most general form of a physical state. The mathematical theorem that's behind that is Gleason's theorem. So let me start with the first of these three reasons. Different experimental setups that correspond to the preparation of different states. Let us consider a source that emits quantum systems. For example, spin 1/2. So this is my source, and it's emitting spin 1/2. And I would like to consider two different scenarios. In the first scenario, I have in my source, I have spins that are all prepared in a certain state, which I call the plus state. It's a linear combination of spin up and spin down. It's a superposition of spin up and spin down. And all the spins in my source are prepared in this superposition state. So whenever I emit a spin, whenever the source emits a spin, it's in this superposition state. And I would like to contrast that with the situation where in my source I have a collection of spins, and half of these spins are prepared in the spin-up state, and half of the spins are prepared in the spin-down state. So in my source I have spin-ups, and I have spin-downs, and I know that 50% of my spins are prepared in spin-up, and 50% in spin down. And my source randomly picks one of these spins and randomly emits one spin. So whereas in the first case, I know the spin that is emitted by the source is in a superposition state of spin up and spin down. In the second case, all I can say is that the spin that's emitted by the source is with 50% probability a spin up and with 50% probability a spin down. Now let's calculate for these two scenarios, let's calculate the expectation value of the z component of Pauli spin and the expectation value of the x component of Pauli spin. In the first case, the expectation value is given in this form. We have to sandwich the Pauli z operator in between the superposition state. And when you insert the superposition states here, you find that this expectation value is 0. In contrast, what do you have to do in the second case? In the second case, I have, with 50% probability, I have a spin up. In that case, the expectation value of sigma z would be spin up, sigma z, spin up, which is equal to 1. With 50% probability, I have a spin down. In that case, the expectation value would be spin down, sigma z, spin down. This expectation value would be equal to -1. Now, the overall expectation value is I have to take the weighted average of these two possibilities. So I have to multiply the first expectation value with probability 1/2, because with probability 1/2 I have a spin up. And I have to multiply the second possibility also with 1/2. And then I take the weighted average. And this is again 0. So with respect to the z component of spin, the two scenarios agree in their expectation values. Now let's look at the expectation value of the x component. In the first case, again, we sandwich Pauli x between the superposition states. And you can convince yourself that this is equal to 1. In fact, the superposition state is an eigenstate of the x component of Pauli spin with eigenvalue 1. In the second scenario, we have to apply the same logic. We have to calculate the weighted average. So 1/2, and then the expectation value of sigma x in the spin-up state, plus 1/2 the expectation value of sigma x in the spin-down state. It turns out the expectation value of sigma x in the spin-up state is 0. The expectation value of sigma x in the spin-down state is also 0. And the weighted average, therefore, is also 0. So here, the predictions disagree. The first scenario and the second scenario, in the two scenarios, I have different expectation values for sigma x. Now this is mathematical evidence that I have different states here. And it's also plausible because physically I have different preparations of my state. In the first case, I prepared a superposition state. And in the second case, I randomly pick a spin-up state or a spin-down state. These are physically two different ways of preparing a state. In the first case, I have a pure state, namely the superposition state. And what I have in the second case, that's a mixed state. And here is how the concept of a density matrix arises. Let me sketch again the two scenarios. So the first scenario where I emit a superposition state. When I calculate the expectation value of an arbitrary observable A, so A is an arbitrary observable. What do I do in the first case? I sandwich A between the pure state plus the superposition state. And we learned before that I can also write this as a trace over projection operator onto the plus state times observable A. In the second scenario, where I have 50% up and 50% down, in the second case, how do I calculate the expectation value of an arbitrary observable A? I take the weighted average. I calculate the expectation value in the spin-up state and the expectation value in the spin-down state. And I take the weighted average of the two with corresponding weights 50%. The first expectation value in the spin-up state, again using our general result from before, can be written with the help of a projection operator. I can write this as 1/2 the trace of projector onto the spin-up state times A. And the second term I can write as 1/2 trace projector onto the spin-down state times A. I can combine these two expressions, can write this as the trace of, and then I have 1/2 projector spin up plus 1/2 projector spin down times A. And this term here in the round bracket, I call this rho. And this rho is the so-called density matrix. And here you see how the density matrix generalizes the projector. In the case of a pure state, we had, for the expectation value of an arbitrary observable, we had the form, it's the trace of projector times observable. And now, where we have a mixed state, the expectation value has the form trace of density matrix times observable. So this is the generalization. We go from a projection operator for the state to a density matrix for the state. The density matrix is also known under a different name. It's also sometimes called the so-called statistical operator. And what's important is that it's different from a projector. Yeah, so rho is different from a projector, and it describes a mixed state. So the way we encountered the density matrix was by saying that the expectation value of an arbitrary observable A can be written in the form trace density matrix times this observable A. In particular, remember the other place where projection operators appeared, namely the probability for obtaining a certain eigenvalue. Yeah? So remember the probability of finding a certain eigenvalue AI for an observable, that was equal to the expectation value of the associated projector onto the associated eigenspace. And this too we can now write in the form with the density matrix. So the probability of finding a certain measurement value AI for an observable A is now given by the trace density matrix times projector onto the associated eigenspace. This helps us to find a number of useful properties of the density matrix. First of all, this probability for finding expectation value, eigenvalue AI, this probability must always be a real number. Probabilities must be real. Now, if the probability can be written in the form trace rho times pi, and this must be real for arbitrary projectors pi, this is only ensured if the density matrix rho is Hermitian. Secondly, probabilities are numbers between 0 and 1. In particular, probabilities are never negative. They're always larger or equal to 0. This implies this is only ensured if the density matrix is itself a non-negative operator. It has eigenvalues larger or equal to 0. It has non-negative eigenvalues. And finally, probabilities are normalized to 1. So if I measure a certain observable, then I know for sure that I will find one of the eigenvalues, exactly one of the eigenvalues of the observable. So if I take the probability above for finding a specific eigenvalue, I sum over all the possible eigenvalues, then this must be equal to 1. And this is ensured if the trace of the density matrix is equal to 1. So these are the three basic properties of a density matrix. In fact, any operator that satisfies these three requirements, permission, non-negative, and trace equal to 1, qualifies as a density matrix. Now, from these properties, we can deduce a number of further properties. Being Hermitian, there must be a spectral decomposition. So it must be possible to write rho as a linear combination of eigenvalue rho I times associated projector pi, where the eigenvalues are all non-negative and they add up to 1. That's the normalization condition. Now you see from this spectral decomposition that a density matrix can always be written as a linear combination of projection operators. And that's in fact the form in which we first encountered the density matrix in our spin example. In that case, the density matrix was 1/2 projector spin up plus 1/2 projector spin down. So it was a linear combination of projection operators. And this spectral decomposition shows that you can always write a density matrix as a linear combination of projection operators. Now, another property, when you take the square of a density matrix and you use the spectral decomposition, then this is equal to eigenvalue rho k squared times associated projector pk. Now the eigenvalues rho k are numbers between 0 and 1. If you take a number between 0 and 1, you take the square of that number. The square is always less or equal the number itself. It's equal only if the number is 0 or 1, but if it's between 0 and 1, then the square is always smaller than the number itself. So this is always less or equal sum over k rho k pk, which is equal to rho. So in other words, rho squared is smaller or equal rho. It is equal, you have equality if and only if the eigenvalues of rho are all 0 or 1. And there is only one situation in which this happens, namely if rho is a projector. And in other words, if the state is pure. Yeah? So you have pure states are included as a special case. In that case, the density matrix is simply the projector onto this one-dimensional subspace spanned by the vector psi. This projector satisfies all the properties above. It's Hermitian, it's non-negative, and it has trace 1. And the square of a projector is the projector itself. It's idempotent. We had this property before. And in fact, you can use that as a criterion to check whether a density matrix describes a pure state or not. A density matrix describes a pure state if and only if rho squared is equal to rho. Yeah? So you can use that to test the purity of a state. Because sometimes it's not obvious. You're given a density matrix, it's not diagonal, and you cannot recognize immediately if it's pure or not. Then my suggestion, you simply take the square, and if it's equal to the matrix itself, then it corresponds to a pure state. There are more properties to the density matrix. The other properties I will show you next week.